Happy Monday, Freak Out. If you're watching this, that means you're on the to-do list and you found Hyperbolas, the link on for the notes, and you clicked on it. And we are going to take a deep dive into Hyperbolas, but for now, I want to do a quick review and just remind ourselves of what we've been doing. We talked about conic sections before break and where they came from, that double-napped cone, that hourglass-looking shape, and different slices of it. We had circles, we had parabolas, and we learned about a directrix, and we learned about the focus, the vertex. Then we learned about ellipses, and ellipses had the two focal points, and that's kind of where I wanted to jump off. I gave you guys a stamp to work on, but at the beginning, no, that's not what I want. This is what I want. At the beginning, we talked about, in college, I had that person who got extra credit for doing this up at the board, and I was pretty jealous, but we had two focal points. In this case, that would be the tacks. And then that distance, the sum of, if you add the distance from the first tack to a point on the ellipse, and you add the distance from the other focal point, the other tack to the spot on the ellipse, those are always the same. It ends up being the length of the string. So as I let this thing play, we got a little recording of a recording there. Let's see if I can get a better one. Well, that's okay. I get two of them actually. The distance from focal point to ellipse, focal point to an ellipse, if you add those, it's the length of the string. Focal point to this one, focal point to this one, still the length of the string. That distance is always the same as you go around and make this locus of points, this group of points that make up an ellipse. So that's kind of where we left off with ellipses, and we learned how to find different things of those. What I am going to do now is kind of give you the same idea, but it's new. It's the hyperbola. So let's check it out. Here's the backdrop. Here's the story. There's three friends. Two friends are on the phone with a third friend. They're having a little group conversation. So here is friend number one. Here is friend number two. The third friend calls them on the phone and says, hey, if you guys leave right now and walk straight to me, one of you is going to get here 3 minutes before the other. Okay? Where am I? So they have to figure out where this third friend is. Well, believe it or not, this is going to end up making a hyperbola. So let's take this information down. Let's do the easiest one. If the friend on the phone is right here, okay, they know how fast these friends can walk. The red friend knows how fast the other two friends walk. If they leave right now, this friend will walk, and it will take him, I don't know, 7 minutes. That means this friend would walk, and it would only take him 4 minutes, because on the phone call he said one of you is going to be here 3 minutes before the other. That would be a place where they could go looking. That's the place they could go find him. Well, another place this friend could be maybe is right here. So this friend now, when he walks, it would take him, I don't know, 7.5 minutes to get there. It's a little bit further away. This one too is a little bit further away. It would take him 4.5 minutes. Okay, and we can keep going this route. What if the friend could be here? So it could take, I don't know, let's say 15 minutes for him to get here. That means it would take this friend 12 minutes. Okay, and we have this idea of symmetry. If it's happening going up, it could be the same thing going down. Okay, and I could draw one extreme one, maybe way over here. It would take this friend 100 minutes to walk and make it to this friend, and it would take this friend 97 minutes. Now, as these numbers get bigger and bigger and bigger, relatively speaking to themselves, they're closer together. There's not that big of a difference. Okay, if you rechange a 4 to a 7, I mean it's almost doubling it. But going from a 97 to 100, they're relatively they're close. What that's telling me is, as these distances get further and further away, there's going to be an asymptote. They're going to get closer and closer to this line, but never quite get there because they're always going to be about 3 apart. So I have the makings of the first little leg of my hyperbola. Now, why did we go on this side? That was because this friend was faster than this friend, but it could have been the flip-flop of that. It could have been that this friend was faster than this friend, so in that case, we would get the other arm of the hyperbola. And we have this little shape of our hyperbola, okay? Let's look at another little animation that I found that I thought was pretty nifty here. I'm kind of talking about the same thing. So we have two circles. The thing with circles is their radii is always the same. So as I let this thing play, let's pick one and stop. The reason the friend thing worked with friend 1 and friend 2, so this would be friend 1, this would be friend 2, and this is the friend that called them on the phone. They know that one of these is always going to be 3 units longer than the other. What that's telling us, the difference between these two distances is always the same. So where on an ellipse, if I added the two distances, the sum of those two distances was the same. It's the difference of the two distances here. And let's take a look at this. The distance between friend 1, which is where my mouse is right here, to friend 2 would be radius 1, this is the radius of the first circle, plus radius 2. Okay. The distance from the second friend to that phone caller, the phone calling friend, that's a radius 2. Okay, so radius 1 and radius 2, that's radius 1 plus radius 2, minus, this is a radius 2. Radius 1 plus radius 2 minus radius 2, that's just radius 1, R1, because those two things are going to cancel out. Let's let it play and pick a different one. About like right here. Okay, what if the friend was right there? Radius 1 plus radius 2 minus radius 2. The radius 2's cancel and it will always be that same distance. In our problem with the friends, they were always 3 minutes apart. And I just used time to kind of make a point, but it could be a distance makes more sense to us, right? So let it play, doesn't matter. That to get from this friend to this friend would be a radius 1 plus a radius 2. To get from this friend to this friend, it's just a radius 2. If you subtracted those, you'd get radius 1. So no matter where I draw these circles that are tangent to each other, that distance, the difference between the distances will always be R1, radius 1 in this case. So that's the idea behind a hyperbola and like what the shape is. We're going to move on here with the next part of these notes, and I'm going to show you guys algebraically what that's telling us, okay? So conic section, call this note 3 for us. The hyperbola, set of all points where the difference between the distances to the foci or focal points is always the same. Okay? So if you're a note taker, by all means, take some notes. Don't lose those good habits you guys had just because we're sitting at home and doing this in a hat and a hoodie. Let's have some different habits, but good habits. Okay? Here is the picture. Feel free to pause and write down what you need to write down, but I'm just going to keep mowing through this stuff, or our time is limited on this screencast-o-matic. So we have our 2 focal points. They're in red. Just like in an ellipse, the distance from the center of our hyperbola or ellipse to a focal point, we call that C units. It's going to be C, letter C in all these equations and things. The distance from the center of our hyperbola to a vertex or to the vertices is A units, okay? The distance from the center of our hyperbola to the ends of what we call the conjugate axis, new term right there, is B units. So we still have, you can kind of see an ellipse in all of this, right? If I drew an ellipse, it's not an ellipse though, it's a hyperbola because how we changed our definition up there. But we can still use these same notions, these same ideas of distances. From here to here is A, from here to here is B, from here to here is C. B itself, as I change the shape of B, it's going to change the curvature, and A, but it'll change the curvature of these hyperbolas. Are they going to be really, really wide? Are they going to be narrow? What will the slant asymptote look like? Yes, there is a slant asymptote. So notice some of our new words here. The transverse axis is the axis that connects the 2 vertices from here to here. From here to here A, from here to here another A. It's 2A long. Kind of just like the major axis and minor axis for ellipses. The conjugate axis, that's 2B units long. From here to here, from here to here. We call that the conjugate axis. Now notice that's not really on my hyperbola, but it's going to help us when we end up graphing them, and that's where we're going with this stuff. So we have A, B, and C. On an ellipse, remember it was the non-Pythagorean theorem that related all 3 of these distances, but for us this time, it is just the Pythagorean theorem. So depending on what the problem is, maybe you have to do some work and get A, and I give you C, and you have to find B. Or I give you A and B, and you have to find C. So these are all interconnected, and it's going to feel like ellipses. This is, besides the shape looking different, this is one of the big differences here. We're using the Pythagorean theorem instead of the non-Pythagorean theorem. Okay? Let's try graphing one of these out. Oh, I do have one more little, what does the equation look like? I gave you guys an optional activity over the second week or first week, and a couple of you sent me an email and said, I can't do anything with hyperbolas. I don't know what the equation looks like. Well, here's the equation. The equation almost looks exactly like an ellipse, only there's a minus sign between them, not a plus sign. Notice a couple things about this. The a squared on an ellipse could bounce back and forth between these two, but for a hyperbola, it will always come first. It will always be the positive one. So if it's a side opening hyperbola, if you want to think of it that way, where the arms are going left and right out, the x one will come first, left and right, you want to think of it that way, over a squared, always over a squared. The y one will be negative, minus y something something squared. For the other way, if it's a top opening hyperbola, if you want to think of it that way. In this case, the y term will be positive. A squared still comes first. It's the x's and y's that are flip-flopping, and the h's and k's along with them. So those are our general forms. Put a little star by those in your notes. General form, standard form for hyperbola, apologies. Then here's another picture I was showing you, the difference between these distances. If you took d1 and subtracted d2, that's constant. That's going to be the same value always. I could pick any other point I wanted on here. The distance from here to here and from here to here, if you subtracted those, always the same. Okay, so let's try a problem. And that'll be the end of our first note. There should be 2 videos for this. Getting a little ambitious here. You guys got a whole week, though, to handle this. Let's sketch a graph of the hyperbola. Okay, you've never seen this before. This is new. I don't expect you to hit pause and just rip through this right now. This is a little different, but one thing remains the same. The center. The center of this hyperbola is at a positive 2, sine flip, negative 4. Okay, we got that. So from there, I'm going to switch papers here and go to the next one. Just like an ellipse, if this was an ellipse, if this was a plus sign, we would go from the center and we would go left and right 3 units, and we would go up and down 2 units. We would put those dots and we would connect them, and it would be an oval, it would be an ellipse. We're going to do something similar here, but we're not going to connect those points. So let's check it out. From the center, on our transverse axis, that's the first one, that's the one that's positive. We're going to go left and right 3, and we're going to put dots. That's no different there. In this one, though, on a hyperbola, we're going to go up and down 2, and we're going to put x's. Okay, this is a little different. Not every teacher does this, but I like to do this to remind me. The dots are actually going to be part of my graph. I'm going to draw my lines through those dots. The x's are just going to be helpers. They're going to help me draw what I need to draw and help me with the curvature of this stuff. Remember, that's what the b value was. So if we put our drawings down, this is what we have to deal with. From the center, we went left and right 3, which is A. We went up and down 2, which is B. On the B part of it, we used x's instead of dots, just to remind ourselves that's not really part of our graph. Easy enough? And if this was an ellipse, we would just connect those, but it's not an ellipse. Next, we're going to use these 4 points we just made to draw a rectangle. So I'm going to go, what was up and down 2, so from here I'm going to go up 2, down 2, up 2, down 2, and then I'm going to draw a rectangle. Should look something like this. Okay? The diagonals of this rectangle you just made form the slant asymptotes for our graph. That's what it's going to approach. Clicking down to the last 2 minutes here, so we're going to wrap this up. So I drew my rectangle. I will draw the slant asymptotes. And then just like anything that has asymptotic behavior, our graph will go through the vertices, those dots, and it'll approach the slant asymptote, never quite get there, on both sides, going up and down. Okay, we did it. We graphed a hyperbola. Congratulations. That's video number 1. Click on video number 2 when you're done. Be taking down notes, be writing questions, so you can come see me in office hours and we can go over this stuff. But there'll be a stamp here at the end of this next video. See you in a second.